Hello everyone, this is Ziheng Liu. I'm a third-year PhD student from Tsinghua University, and it's an honor to be here to present our work, Lasagna. And I hope all of you a good appetite after my presentation in the following coffee break. And so let's get started. And here is the outline of my presentation, and first the background. So recently we have witnessed the phenomenal development of smart wearables, and there will also be many promising industries like healthcare, medical, fitness, wellness, commercial, military, and so on. But the reality seems not so satisfying because most of the apps in the App Store, Google Play, many other app market just counterstep and derive your calories, intensity, and some statistics. So from my point of view, I think wearables are far from smart because they don't understand what we do every day. So let's see some potential applications if wearables are smart enough. For individual users, we can keep a smart diary of our activities every day, and we can see how much we work, we run, we play on our cell phones, etc. And for companies, manager can achieve accurate working performance without any supervision. And on the other hand, government and organizations can achieve the investigation on civil health condition, and they can also study the cause of common occupation diseases and provide many suggestions. So in this work, we propose to make wearables smart. And our work, Lasagna, proposes the deep hierarchical understanding of mobile sensing data. And we enable the semantic-based activity search. So before introducing the details, let's see some existing approaches. So existing approaches can be divided into three categories. And the first one, we can build up many models to recognize our handshake and gait. But this kind of approach, the model they build often targets on specific activities, and often they are hard to spread to others. So on the other hand, the feature set-based method is activity independent. We can use statistical features and apply them on the classifiers like SVM, etc., to perform the accurate classification. But this kind of approach adopts the statistical features, and they cannot often provide satisfying results. And the mean accuracy are often about 80%. So recently, researchers use supervised deep learning methods to perform the recognition. And the accuracy can be as high as 98%. But this kind of approach often requires too much training data, especially labeled training data. And also training time and computation resources are required. So here we summarize the challenges. The first is the activity. Our activity are often arbitrary and rich in hierarchical semantics. And the second one comes from the data. The data can be easily affected by the diversities, for example, device, people, time scale, etc. And last but not least is the resource. Our devices are often limited in resources, for example, battery, computation, and so on. So now I will introduce the details of our work. So the first question we must answer is how to describe arbitrary activities. As we all know, we may perform arbitrary activities and there can't be any pre-knowledge. So luckily, we have several inspirations. The first one is the basis. So the basis is one of the most important concepts in linear algebra. And using the basis, we can see that an arbitrary point can be represented by the basis. And for any 2 points, they can be comparable according to the embedding. That is the coordinates. And the second inspiration is the convolutional kernel. So the convolution kernels have been widely used in extracting the latent information, especially from those complex data. And different kernels can reveal different characteristics. So we came up with the idea of adopting kernels as motion bases to form a motion space. By doing this, we can see that for an arbitrary activity, it can be represented by the motion basis. And furthermore, two activities can be comparable according to the embedding in the motion space. So how can we get the motion basis? So in our work, we use the CRBM, aka the convolution restricted Boltzmann machine, to learn the motion basis. So CRBM is a two-layer model, and as you can see, the visible layer and hidden layer. And for the input data, we insert them into the visible layer, and using the inference equation, we can infer the data in the hidden layer. And on the other hand, we can reconstruct the visible layer using the reconstruction equation and the hidden layer data. So more specifically, we can see that by minimizing the reconstruction error, our kernels can be learned through an unsupervised manner. And then, because of the sum operation, if we combine all the kernels WK as a basis, we can see that all the HK can build up the embedding in the motion space. So suppose that we have a piece of data in the left, and using all the convolution kernels, we have all the embeddings H, and we further normalize all the embeddings, and finally we get the semantic descriptor, which is a vector. And furthermore, since both of the convolution and normalization are linearly correlated to the length of the input, we think that it is really computation friendly to our smart devices. So as you can see in this figure illustrates the pairwise similarity between the 11 activities, and our descriptor helps to distinguish different activities. And the second question is that how to address the hierarchical semantic. As you can see in the figure, for the same piece of data, we can have different understanding over the data in different resolutions. So similarly, we have the inspiration of the reception field. The reception field refers to the kernel size. As you can see, the convolution kernel can reveal the characteristics covered by the reception field. So we can find that if we can build the hierarchical reception field, that we can address the hierarchical semantic. So how can we build up the hierarchical reception field? We perform two simple modifications over the basic CRBM. The first, we add a pooling layer P to pull the output of H. And the second, we stack multiple building blocks, the three-layer building blocks, to form a deep model. And the output of the pooling layer can be inserted to the new layer in the higher structure. So with these modifications, we can see that kernels in the higher level can have larger reception field. That is to say, we can combine these descriptors from different levels, and then we can have a comprehensive understanding of our mobile sensing data. And so now let's introduce the semantic-based activity search. The SBAS is to achieve the search by activity. That is to say, I can perform the running operation for a few seconds, then I can retrieve all the running data in the massive database. So there are two remaining problems to solve. The first one is we must get different activity separated. because all the data are continuous in the database. And the second one is requires that the search strategy must be efficient since we have really large database. So to this end, we provide such an architecture and which have 3 components. The first component is the model training component, which is used to extract a hierarchical motion basis and extract the descriptors. And the second one is to index all the activities in the database. And when we insert the search data into the activity search component, we can return all the time spans of the same activity performed by the searcher. So at last, I will introduce the implementation and evaluation. In the implementation, we provide 2 kinds of client applications. One is for Android, Sony smartwatch, and the other is for the Tizen system. And the dataset we use consists of 3 parts. And for dataset 1, we can divide them into the controlled environment and the uncontrolled environment. And the dataset number 2 is an open dataset, which includes 10 different people and 7 activities. So after we learn the motion basis, we use them to perform the typical classification task. And as you can see, our hierarchical descriptor can provide competitive accuracy comparing to the number 14 used the feature set-based method, and the number 15 used the supervised deep learning method. And then we evaluate the performance of SBAS. And intuitively, we have the trade-off is that if we have a larger similarity threshold, we will have a lower precision and a larger recall. So the evaluation is for the data set 1, which is an uncontrolled data set. When the threshold is set to 0.3, we can have an accurate precision of 90% and recall of almost 100%. And for the uncontrolled data set, when the threshold is set to 0.5, we can have both the precision and the recall both at around 80%. And next, we evaluate the efficiency of our system. You can see that it takes seconds to index and search on our toy server, and we believe that it will be optimized by more powerful servers, even clusters. And we find that keeping running Lasagna at backstage only leads to about 10% additional power consumption for our devices. So we believe that it will be coming to reality in the future. And to summarize, in this work, we provide the deep hierarchical understanding and provide a new concept named SBAS, which is the semantic-based activity search. And we believe that there will be many open issues, for example, data preprocessing, including activity segmentation or activity indexing. And moreover, there will be more advanced searching strategies. For example, we can search the activity using our keywords or using our voice. And moreover, there will be privacy issues if we really collect massive data from different people. So thanks. That is my presentation, and please ask.